Hello and welcome to Textbook Engineering Problem. We're looking at Elementary Principles of Chemical Processes, 3rd edition. Today we're going to be doing problem number 2.28. A concentration C in moles per liter varies with time in minutes according to the equation Okay, part A, what are the units of 3 and 2? Okay, so I've explained this in the last 2 episodes. This cannot have units, so this term must have the same units as this term. Okay, so we know that the 3 actually has units of moles per liter. Okay, now the 2 right here has to have reciprocal units of t. So if t is in minutes, then the 2 has to have reciprocal of that so that the units cancel out. Because, like I said, this term cannot have units. Okay, so 2 has to have reciprocal minutes as its units. Okay, part B. Suppose the concentration is measured at t equals 0 and t equals 1 minute. Use 2-point linear interpolation or extrapolation to estimate C when t equals 0.6 minutes and t when C equals 0.10 mole per liter. Okay? So we need to figure out what these equal. Okay, from the measured values, and compare these results to the true values of these quantities. Okay, so first we're going to interpolate or extrapolate, and then we're going to look at what the results are based off of the equation that we have right here, this empirical equation. Okay, so first let's get the values when t equals 0 and t equals 1 minute. Okay, so C at t equals 0 equals 3 moles per liter, and C at t equals 1 equals 0.406 moles per liter. And again, I got both of those values just by plugging 1 in for t and 0 in for t, and then calculating what it was using that equation. Okay, now we're supposed to do linear interpolation, 2-point linear interpolation or extrapolation to estimate based off of these 2 points. Okay, so let's do our interpolation here. We have to make a line, y equals mx plus b. The slope equals y1 minus y2 over x1 minus x2, and b, the intercept, equals x2 y1 minus x1 y2 over x2 minus x1. Okay, so the slope of this line equals minus 2.594. Well, let me back up here, just so you guys know what y1 and y2 are. y1 is this, or I'll color code them. Y1 is this, Y2 is this, X1 is this, and X2 is this. That's why we calculated our points. So we have 2 points. Each point has a y coordinate, an x coordinate, and a y coordinate. And I just showed you how we calculated those. Given a certain x, we have a certain y based off of the function that we were given, and then those correspond to 2 points, and the 2 points fit into this formula that I just wrote down right here. That's the equation of a line, and that's what interpolation is. It's linear interpolation, so you're just assuming that all the points fit on a line, and you estimate what the values are based off of fitting the points to 2 points on the line. So now our equation looks like a line instead of like the exponential function that it is. So it's just a way of estimating. Let's say, for instance, we didn't know what the exponential function was. Well, if we didn't know what those were and all we had were these data points right here, well, then we could estimate what the function was by assuming that it was a line instead of an exponential function. And I'm assuming that this problem will go into, well, how accurate is that assumption that you make? And sometimes it can be pretty close if you're not going too far away from your values, because you know that these values are exact for y1 and y2. If you go too far away from those points, though, your values that you calculate are not going to be very good. So, okay, so we calculated what the slope was, and b equals 3. So now we need to do a linear interpolation, but now instead of using our original exponential function, now we use our linear function. We have our parameters here, m and b, defined, and so now we can calculate an estimated value of y, which is equal to like our c estimate. So now we say, what does our c estimate equal when t equals 0.6? So c equals 1.44 moles per liter. And our t estimate, using our function in reverse, so instead of saying x is equal to t, now we're reversing it. So now we have our t estimate equals this, where y is our given c value, 0.10 moles per liter, and that equals 1.118 moles per liter. Okay, so those are our 2 estimated values using linear interpolation and extrapolation. Okay, and the problem statement said, compare these results with the true values of these quantities. Okay, so the true value of these quantities is 0.904. Sorry, I made an error right there. That is time in minutes. And then our true t value for when c equals 0.1 So we can use this function to calculate what t is given a certain c. So we plug 0.1 into this function, and t equals and now we look to see how close our estimates are. So our estimates are up here, and the actual values are here. How close are they? Well, when we were interpolating, which is when we calculated the concentration when the time equals 0.6 minutes, we're interpolating between the 2 points, and our estimate is actually pretty good, not too far off, but our estimate, when you're extrapolating, it can be significantly off. That's the case in this case where the time is almost double what it was. But in both cases, the estimates are not great. So there you have it. It's a way to get values that are close. They're in the same order of magnitude, but they could be significantly off, especially if you start extrapolating. All right, so that's it for part B. We've looked at the quantities that it asked us to. So now we can move on to part C, where it says, sketch a curve of C versus T and show graphically the points you determined in part B. Okay, so let's take a look at the graph. Okay, so this is C and T. So, and this is T. This is 1, this is 0. So we've got a exponential curve that kind of comes along like this. And right at this point, we have that t equals 0.46, or sorry, right at where t equals 1, we have that the concentration is 0.46. And then we also had that right at when t equals 0, the concentration is 3. Okay, then in part B, we drew a line between these points. We estimated the value of the true function, here highlighted in yellow, by calculating what the values were on the linear approximation of the line. You can see here as the line extends further away from our estimation points, it goes away from the true value pretty rapidly. So when we're extrapolating beyond that point, our value can be significantly off. So in this case, we looked at, okay, what is the concentration when we estimate that the time is 0.6 minutes. Well, we got that it was about 1.44. So now we come back here and we say, okay, it's 0.6. It's about right here. Well, that is a little high from the true value, right? So our error is going to be a little above what it should be. And is that the case? Yeah, it's a little high. Our C estimate is a little higher than what we got. Then we estimated based off of concentration, and we were beyond our estimation here. We still had a positive value, but our estimated value for the time is going to be pretty far off from the real value, and so it should be a lot shorter actually than the actual time. So the estimated time is 1.118. So yeah, it's quite a bit shorter than the real time that we got. And that's because the line just rapidly goes away from our estimate as we extrapolate beyond the points. All right, so that is it for problem number 2.28. Thanks for joining me. If you have any questions about this, put them in the comments. I'll try and respond and clear things up. If you have any problems that you're working on that you need help with that are part of this book, I can write something up and see if we can address that and help you out. Otherwise, thanks for joining me, and hope you have a nice day. Talk to you later. Bye.